Hello, everyone. Welcome to today's webinar. I'm Jeff Huber, contributing editor at Chemical and Engineering News, and I will be moderating today's event. This webinar is titled Obtain Increased Sensitivity and Solvent Savings with New 1.5 millimeter UHPLC columns, and is being sponsored by Advanced Materials Technology. CNEN works with sponsors to identify topics of interest and value to CNEN's audience, and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen, or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNEN online after the live webcast. The presentation today is being sponsored by Advanced Materials Technology. AMT is an innovative product development and HPLC column manufacturer focused on improving the presentation of the sample to the detector. From pioneering fused core technology in 2005, the Halo product line has changed previous conventional wisdom that high resolution requires high back pressure. Now in its 17th year, AMT continues to be a leader in novel, superficially porous particle development, enabling high efficiency and reliability for scientists involved in both small and large molecule separations, and delivers applicated solutions designed to meet specific industry challenges. The team at AMT is committed to being the leader in on-time delivery and providing technical support expertise for chromatography challenges. And during the presentation, we will hear from Dr. Stephanie Schuster, Senior Technical Support Scientist at Advanced Materials Technology. Dr. Schuster earned her Ph.D. under the guidance of Professor Joe P. Foley at Drexel University. She joined Advanced Materials Technology in June 2009 as a research scientist working with Dr. Jack Kirkland, providing contributions to the commercial development of products designed for peptide and protein separations. Most recently, as part of the technical support team at AMT, Dr. Schuster has been providing customer support in optimizing and troubleshooting their applications. And with that, I will now hand things over to Dr. Schuster.
Thanks for the introduction, and thanks to everybody who's joining us today. First, I'll start with a brief outline of the presentation. I'll talk about the desire to move to smaller ID columns. Then I'll go into the benefits of the smaller IDs with novel 1.5 millimeter ID UHPLC columns, and then we'll finish up with a question and answer session. Before I get into the presentation, here's a poll question. Generally, which column IDs do you use in your methods? Select all that apply. 1 millimeter and smaller, 2.1 millimeter, 3 millimeter, or 4.6 millimeter. Again, we'd like to know generally which column IDs do you use in your methods. Select all that apply. 1 millimeter and smaller, 2.1 millimeter, 3 millimeter, and 4.6 millimeter. First, I'll start with the background to the move to smaller ID columns. HPLC columns were originally 4.6 millimeter ID, operated at 1 mil per minute and above. Then 3 millimeter ID columns were introduced as a means to save solvent. So about 50% solvent could be saved going from a 4.6 by 100 millimeter column operated at 1.5 mils per minute to a 3 by 100 millimeter column operated at 0.8 mils per minute. Then short columns with 2.1 millimeter ID were introduced for use with UHPLC and for interfacing to mass spectrometers. So the impact of smaller ID columns include the following. The effects of viscous friction are diminished. The signal intensity is increased when the same sample concentration is used, and you're operating at a lower flow rate, so less solvent is consumed, which means reduced consumable and waste disposal costs. So now I'll discuss the fundamental effects in transitioning to smaller internal column diameters, and the first topic will be viscous friction. So we have the formation of thermal gradients due to viscous friction, and the heat that's generated from these thermal gradients can be measured by the power equation at the top of the slide, where power equals the flow rate times the pressure drop. And we have two different kinds of temperature gradients. On the left-hand side is an example of axial gradients, which are less reproducible in terms of elution time. On the right-hand side, you have the radial gradients, which give lower efficiencies when you're generating approximately 4 watts per meter and above. And we'll talk about each of these in more detail over the next couple of slides. First, let's examine the formation of axial thermal gradients due to viscous friction. And here the column is cooler at the inlet, represented by the blue color, and hotter at the outlet, represented by the red color. These axial thermal gradients are maximized in quasi-adiabatic environments. And that means we have either an insulated column or a still air oven condition, which means no convective movement from the oven fan. So if you turn your attention to the plot of retention factor versus flow rate, you can see the results for the column oven are in the red squares. And as you increase flow rate, you can see how the retention factor is reduced. And that's happening because at those faster flow rates, more heat is generated, which is making the peak elute at a shorter retention time. And you can compare that to the result in the blue squares, which is the column operated under flowing water jacket conditions. And across the different flow rates, you can see how the retention factor is consistent over the entire range. So what you have is higher efficiency, but also higher differences in retention time across that flow rate range, which could impact the run-to-run reproducibility. Now let's examine the formation of radial thermal gradients due to viscous friction. Looking at the column diagram here at the top of the slide, you can see that the center of the column is hotter, whereas the outside of the column is cooler near the wall where the heat can escape. Radial thermal gradients are maximized in quasi-isothermal environments, and this is where you have air or water jacketed columns or forced air oven conditions. In particular, you do have convective movement from the oven fan, which helps to cool the outside of the column to make that radial thermal gradient happen. So looking at the Van Deemter plot on the left-hand side of the slide, you can see for the column operated under the flowing water jacket conditions for the blue trace, you can see that as you go to higher linear velocities, you also have higher reduced plate heights, which means a loss in chromatographic efficiency. Comparing that to where you have the column oven in place, you can see how at the higher linear velocities, you also have lower reduced plate heights. So you have the opposite condition as what we had described on the previous slide. In this case, it's lower differences in retention time across the flow rate range, but you're also seeing lower efficiency. What are the considerations for reducing viscous friction? Well, we can consider using smaller internal column diameter. Here's a table of column inner diameter going from 4.6 millimeter down to 50 micron. The flow rate is going from 2 mils per minute down to 240 nanoliters per minute. The pressure is kept constant at 7,000 bar, and the power is calculated here where the flow rate is multiplied by the pressure drop. So you can see the power is going from 24 watts all the way down to 2.9 milliwatts. And 24 watts is enough power to boil the mobile phase before it exits the column. So of course, we don't want to operate under those conditions. So if we're able to reduce the flow rate, which is reducing the viscous friction, this creates an incentive to use the small ID columns to minimize that viscous friction effect, especially for high throughput separations. The next fundamental effect we'll look at for transitioning to smaller internal column diameters is peak signal. So, internal column diameter and concentration sensitive detection. Most LC detectors are concentration sensitive. The limit of detection is improved when the LC delivers a highly concentrated sample. So we want to minimize dilution of the sample in the mobile phase. The flow rate optimum scales with the ratio of the square of the radius of the column. So for example, going from a 4.6 millimeter to a 1 millimeter ID column, the flow rate would change from 1 mil per minute to around 50 microliters per minute. And this would represent a 20-fold enhancement of the signal potentially, depending on extra column volume effects. This calculation is based on identical sample load, which means the same sample concentration and injection volume. Now let's look at a comparison of absorbance signal as we vary column diameter. On the left-hand side, we're starting with a 2.1 millimeter ID column, and the maximum absorbance is 0.25 absorbance units. As we reduce the column ID to 1.5 millimeter, we can see that the absorbance increases to 0.35 absorbance units. And then decreasing the column ID to 1 millimeter, we can see how the maximum absorbance is 0.47 absorbance units. So we're seeing a trend of increased signal as the column ID decreases with identical sample load on column. So the last fundamental effect we'll look at in transitioning to smaller internal column diameters are extra column effects. Now let's look at the sources of extra column band broadening. Here we have a basic diagram of a UHPLC system with a total dispersion including all the elements inside the dashed black square. So we have the sources of extra column band broadening now highlighted, with the yellow being pre-column, which consists of the sample injector and the pre-column tubing, and the red being post-column, which includes the post-column tubing and the flow cell or the ionization source. Both of these sorts of volumes or contributions need to be optimized or minimized in order to get the best out of your UHPLC column. Now let's look at the pros and cons in shifting from 2.1 millimeter ID to 1 millimeter ID. On the left-hand side, we have a comparison of the results of a separation of alkyl-phenones run on 2.1 millimeter, a 1.5 millimeter, and a 1 millimeter ID column. And we can see that we have that higher signal intensity as we go to smaller column ID, and of course the viscous friction decreases. But if you turn your attention to the right-hand side of the slide, there is a significant loss in efficiency for the 1 millimeter column, which is showing plates of 7,600 compared to a result of 16,400 for the 1.5 millimeter ID column and 17,600 for the 2.1 millimeter ID column. And this is really caused by extra column effects. So the 1.5 millimeter ID columns can provide a compromise between these effects. So as a summary for this first section of the presentation, we've seen that smaller ID columns are less subject to the effects of viscous heating. Smaller ID columns offer benefits of increased signal and reduced solvent consumption. However, to realize the benefit of increased signal, the impact of extra column effects of the UHPLC and or MS system being used must be minimized. Now we have another poll question. How frequently do you consider your LC system configuration when selecting column ID? Often, sometimes, or never? Please select your answer. Again, that's how frequently do you consider your LC system configuration when selecting column ID? Often, sometimes, or never? Please select your answer. Here we introduce a new dimension in separations. With the new Halo 1.5 mm ID, we bridge the gap between analytical and microflow columns. This is a modern-day proposition for Halo. In 2006, Halo particle technology enabled separation scientists to use their conventional LC systems to discover the benefit of higher efficiencies of sub-2 micron fully porous particle packings, but without the back pressure consequences and investment in UHPLC systems. In 2022, Halo innovates with a new SPP column dimension to deliver more performance from adopted UHPLC systems in terms of sensitivity and reduced solvent consumption without the investment of specialized instrumentation and more challenging operations. So let's talk about the benefits of the new Halo 1.5 mm ID columns. So what benefits do the 1.5 mm ID columns offer? More performance from UHPLC and LC-MS systems, including more sensitivity from conventional UHPLC systems, higher ionization efficiencies from LC-MS systems, reduced solvent consumption compared to 2.1 mm ID columns and greater, which translates to reduced waste disposal costs and a smaller chemical footprint, and an easy-to-implement microflow solution with existing systems. So there's no need for buying expensive and specialized capillary or nano systems, and the columns are robust and easy to use compared to capillary and nano columns. First, let's talk about more sensitivity from conventional UHPLC systems. Here I have a comparison of an over-the-counter cough and cold medicine separation run under gradient conditions. The orange trace shows the 1.5 by 150 mm Halo C18 column results, and that's compared to the blue trace, which shows the results run on the same column in 2.1 by 150 mm dimension. The areas are about 2 times larger with the 1.5 mm ID column, and the peak heights are 1.7 times taller with the 1.5 mm ID column. Here we have another example of more sensitivity from conventional UHPLC systems. In this example, we're looking at a comparison of a separation of peptides and small proteins run under gradient conditions. The orange trace shows the results from the 1.5 by 150 mm column packed with Halo 160 angstrom ESC18, and that's compared to the blue trace, which is the 2.1 by 150 mm column of the same packing material. And similar to the results that we saw for the cough and cold medicines, we're seeing on average about double the area for the results from the 1.5 mm column, and we're also seeing, of course, a more intense response from those 1.5 mm results. Here's an example of enhanced impurity identification. This is an isocratic separation of acetaminophen, caffeine, aspirin, and salicylic acid, with salicylic acid being an impurity of aspirin. The top trace shows the results on a 3 mm Halo C18 column compared to the bottom trace, which shows the results on the Halo C18 column in 1.5 mm ID. And what we can see is both the area and peak height are increased for all the results on the 1.5 mm ID column. This could be really important for people doing low-level impurity identification. Here we're showing higher ionization efficiencies from LC-MS systems. This is an intact trastuzumab separation using Halo 1000 angstrom diphenyl in 1.5 mm ID by 150 compared to 2.1 mm ID by 150. And we've operated the 1.5 mm ID column at 0.2 mils per minute compared to 0.4 mils per minute on the 2.1 mm ID. The area is 2.9 times larger and the peak height is increased for the results on the 1.5 millimeter ID column. Here we have another example of higher ionization efficiencies from LC-MS systems. In this example, we're looking at reduced and alkylated trastuzumab using Halo 1000 angstrom diphenyl. The top tick shows the results on the 1.5 millimeter ID column, while the bottom trace shows the result on the 2.1 millimeter ID column. The light chain area is 2.7 times larger, while the heavy chain area is about 2.3 times larger than the result on the 2.1 millimeter ID column. Again, the peak intensities are larger on the 1.5 millimeter column compared to the 2.1 millimeter ID column. Now I'd like to switch to some small molecule LC-MS examples. On the left-hand side are the results run on a 2.1 millimeter Halo C18 column for norfentanyl and fentanyl, compared to the right-hand side, which are the results run on a 1.5 millimeter Halo C18 column for the same two analytes. We injected 1.5 microliters of a 2 nanogram per mil sample of each analyte on both columns. And what we saw was a 2.5 gain in intensity and a 2.4 gain in area for the results for norfentanyl on the 1.5 millimeter ID column. For fentanyl, we saw a 2.6 gain in intensity and a 2.4 gain in area. In order to obtain these results on the 1.5 millimeter Halo C18 column, we needed to optimize the source conditions, which included reducing the sheath gas and also reducing the capillary temperature and the auxiliary heater temperature. This next example uses vitamin D metabolites. On the left-hand side are the results on the 2.1 millimeter Halo C18 column, compared to the right-hand side, which showed the results on the 1.5 millimeter Halo C18 column. We injected 1 microliter of 500 part per billion each analyte onto both columns. And for the 25-hydroxy D3, we saw an intensity that was 3 times larger and an area that was 2.9 times larger with the 1.5 millimeter ID column compared to the 2.1 millimeter ID column. For the 25-hydroxy D2, we saw an intensity that was 2.3 times larger and an area of 2.2 times larger. We believe these slight differences in increases can be attributed to differences in the ionization efficiencies of these two vitamin D metabolites. Now I'd like to show some examples of reduced solvent consumption. In this example, we're comparing to a 2.1 millimeter ID column, and the sample was a peptide map of trastuzumab. The orange trace are the results on the 1.5 millimeter ID Halo ESC18 column, whereas the blue trace is the Halo ESC18 column in 2.1 by 150 millimeter dimension. For a 60-minute runtime, the 2.1 millimeter ID column uses 24 milliliters of solvent compared to only 12 milliliters of solvent for the 1.5 by 150 millimeter column. This represents 50% solvent savings, and in addition to the solvent savings, also less waste is generated, which would lead to lower waste disposal cost. The 1.5 millimeter ID column shows increased signal intensity, which is an advantage for low abundance peptide fragments. Here we're showing a reduced solvent consumption comparison to a 4.6 millimeter ID column. And in the example here, we're looking at an isocratic separation of 13 cannabinoids. The gray trace was run on a 4.6 by 150 millimeter Halo C18 column compared to the orange trace, which is run on a 1.5 by 150 millimeter Halo C18 column. For a 10-minute runtime, we're using 15 milliliters of solvent with a 4.6 millimeter ID column compared to only 1.6 milliliters for the 1.5 millimeter ID column. This represents 9.4 times solvent savings if you would go from a 4.6 millimeter to a 1.5 millimeter ID column. And of course, the signal intensities are much higher on the 1.5 millimeter Halo C18 column. Next, I have an example of reduced solvent consumption when modernizing methods. We've taken the USP method for estradiol, which the original method calls for a 3.9 by 300 millimeter column run at 1 milliliter per minute for a runtime of 8 minutes. That would give 8 milliliters of solvent used for each injection. And we modified it to be run on a 1.5 by 100 millimeter Halo C18 column at a flow rate of 0.2 milliliters per minute for a reduced runtime of 1.5 minutes, which gives a volume of 0.3 milliliters per injection. And this represents 96% solvent savings, which is a significant amount when you consider both the cost of solvent and the cost of waste disposal. Next, we have some stability experiments that we ran with the 1.5 millimeter ID columns. In this example, we used the Halo 1000 angstrom diphenyl, and we ran it at 600 bar for 1,000 injections. We observed no loss in efficiency or retention over the course of the experiment, and you can see that here from the comparison of the initial injection to injection 1000. Here we have another example of 1.5 millimeter ID stability. In this case, we used Halo 90 angstrom C18, and again we ran it for 1,000 injections at 600 bar. And from this plot of retention factor versus injection volume, you can see that the retention factor of naphthalene was stable across all the injections, and we had a percent RSD of 0.28%, which represents hardly any change over the course of those 1,000 injections. Next, I'd like to describe the Halo 1.5 millimeter ID column hardware reproducibility. We saw excellent reproducibility from 3 different lots of column hardware, and the different lots are represented by the black, red, and blue traces of this comparison using the over-the-counter cough and cold medicines. The retention time percent RSDs were all 1% or lower, which shows great reproducibility across the 3 different lots of column hardware. Next, I'd like to describe how the 1.5 millimeter ID columns are easy to implement for a microflow solution. The columns look and feel like a 2.1 millimeter ID Halo column. Successful implementation requires system optimization via the hardware and accessories, and I'll talk about both of these in the next few slides. And now we have our final poll question. What would motivate you to use a smaller column ID? Please select all that apply. Increased sensitivity, solvent savings, or ability to use on a standard UHPLC system. Please make your selections. Again, the question is, what would motivate you to use a smaller column ID? Select all that apply. Increased sensitivity, solvent savings, or the ability to use on a standard UHPLC system. So in order to have success using the Halo 1.5 millimeter ID columns, you need to have a low dispersion UHPLC system, short length and small ID connecting tubing, which would go along with that low dispersion system, and then know how to do the method transfer to a 1.5 millimeter ID column. Now let's talk about variance charts run under gradient conditions. Last year, there was a great 4-part series in LCGC North America from Dwight Stoll, Thomas Lauer, and Ken Brockhoven entitled Where's My Efficiency Gone? Impacts of Extra Column Peak Broadening on Performance. And in that series, they introduced this web-based dispersion calculator, which is how we generated the plots on the right-hand side of this slide. So the top shows the standard plumbing under gradient conditions, where the yellow is the dispersion associated with the column, the blue is the post-column tubing dispersion, and the gray is the detector. And this corresponds to the chromatography on the left-hand side of the slide, where we had run the cough and cold medicines on a 1.5 millimeter ID column, and we saw a height of 66 milliAU for peak 8 with a width of 0.046 minutes. When we optimize the system, what you see in the orange trace, peak 8 shows a height of 105 milliAU and a width of 0.037 minutes. And the corresponding variance chart on the right-hand side shows a much bigger pie slice for the column in yellow, smaller post-column tubing slice, and a smaller slice for the detector. And what that means is we're seeing more of the true efficiency of that 1.5 millimeter ID column. So in order to get the most out of the small ID columns, we have to minimize the dispersion as much as possible. In order to help customers reduce their dispersion, AMT is offering Marvel Exact connectors. The difference between Marvel Exact and ferrule fittings is shown in the two images in the center of this slide. On the left-hand side, you can see a Marvel Exact fitting, which shows a flat sealing face, and that gives zero dead volume as it's connected into the inlet or outlet of the column. Compare that to the right-hand image, which shows a ferrule fitting, which sometimes could introduce extra internal volume if the capillary isn't bottomed out properly into the column inlet or the column outlet, and that could lead to reduced efficiency or skewed peak shapes. These connectors are available in both peak sill and peak line stainless steel options. The peak sill we recommend for connections from the column outlet to the mass spec source, and the peak line stainless steel we recommend for connections from the sample injector to the column inlet. The volume is included with the dimension for easy selection. So, for example, a 75 micron by 600 millimeter connector has a volume of 2,650 nanoliters. So, how does one transfer a method to a 1.5 millimeter ID column? The first step is to scale the flow rate, and I have the equation here where F2 is the scaled flow rate for the 1.5 millimeter ID column, F1 is the original flow rate, and that's multiplied by pi r sub 2 squared divided by pi r sub 1 squared. So those pi's cancel out, and you're left with r, which stands for radius, but instead of radius, we substitute out diameter. So D2 is the column ID being transferred to, or the 1.5 millimeter in this case, and D1 is the original column ID. So here I have a table of column IDs going from 4.6 down to 1.0 millimeter, and that's with its associated flow rates in milliliters per minute. So for a lot of the examples that we looked at earlier in this presentation, we're using 0.2 mils per minute for the 1.5 millimeter ID column and 0.4 mils per minute on the 2.1 millimeter ID column. And then you can see how the other flow rates scale on the different column IDs. The next step is, if it's a gradient method, to add an injection time delay to account for the dwell volume. And then finally, scale the injection volume to maintain signal or keep the same injection volume for increased signal. So in the applications that we showed earlier, we kept the same injection volume to show that sensitivity increase. So this example shows the benefits of fused core in a 1.5 millimeter ID column. For both of these experiments, we ran a 1.5 by 100 millimeter Halo C18 column, and this is the same separation of cough and cold medicines that we had looked at earlier. The top trace shows the gradient run at 0.2 milliliters per minute, and it's generating 268 bar back pressure for a total runtime of 6 minutes and a resolution of 5.4. The blue trace shows where we doubled the flow rate to 0.4 milliliters per minute for a back pressure of 524 bar and a runtime of 3 minutes, and the resolution only slightly decreases to 4.3. So overall, we're showing a separation that's 2 times faster with minimal loss in resolution. And this is the benefit of FuseCore in a 1.5 millimeter ID column. You're able to run 2 times faster and still maintain that resolution. What products are available for the Halo 1.5 millimeter ID? We have the chemistries and pore sizes available for small molecules, peptides, and proteins. And these include the Halo 90 angstrom C18, the Halo 160 angstrom ESC18 for peptides, the Halo 1000 angstrom C4 and 1000 angstrom diphenyl, which are good for proteins and monoclonal antibodies. So in summary, I've shown more sensitivity from conventional UHPLC systems with the 1.5 millimeter ID columns, higher ionization efficiencies from LCMS systems, reduced solvent consumption compared to 2.1 millimeter ID columns and larger, an easy to implement microflow solution with existing LC systems. The 1.5 millimeter ID columns are made by a trusted manufacturer of FuseCore columns in a 9001 ISO certified facility, and they're available in chemistries for small molecule, peptide, and protein separations. At this point, I'd like to thank our collaborators, Jim Grinius at Rowan University and Justin Godino at GSK, who were both instrumental in helping us develop the 1.5 millimeter ID columns. I'd like to thank you for your attention, and I'd be happy to answer any questions you may have.
All right. Thank you, Dr. Schuster, for that presentation. And thank you, audience, for submitting questions during the presentation. If you have a question and you haven't submitted it yet, please feel free to do so. We can still get to it. And let's get to some of these questions that have come in. Let me pull that up here. All right. So, Dr. Schuster, here's a question. Somebody asks, does the loading capacity of the column get affected by the internal diameter of the column?
Oh, sure, yes. So that's a great question. The loading capacity will be reduced by, the square of the ID of the column. So just like we have to lower the flow rate and the injection volume when we're moving to the 1.5 millimeter ID columns, the loading capacity is going to be decreased by about the same amount. So if you're on a 2.1 millimeter ID, going to the 1.5, it'll be reduced by about 50%.
Another question that came in here asks, what kind of flow rates could you use on a 1.5 millimeter column if you are running on an HPLC? Wouldn't that back pressure be too high?
Well, that's another good question. It really depends on what kinds of system pressure you have, whether the back pressure would be too high. And we probably wouldn't recommend running on an HPLC unless the dispersion were pretty low. So, in fact, for the experiments that we had run, we were going from anywhere from 0.2 milliliters per minute up to, I've run it at as high as 0.5 mils per minute. So I know it's not, I can't give you like a hard and fast answer, but it really depends on what kind of tubing is in that HPLC or UHPLC, because that's going to impact the back pressure.
Another question that came in asks, how much extra column dispersion can a 1.5 by 100 millimeter column tolerate?
Okay, so that's another answer that kind of depends on what you're looking at. For our system, we were able to reduce the dispersion down to 2 microliters squared, and that gave us the expected efficiency that we were looking for with a retention factor of around 6. So you have to have a decent amount of retention of your analyte under, isocratic conditions in order to see what I like to call the true efficiency of the 1.5 millimeter ID column.
Another question asks, how is retention time related to the size of the column?
For that one, really, if you're thinking about, transferring a method from a 2.1 millimeter ID to a 1.5, and you use the same linear velocity, then you will get about the same retention time. So it all depends how you transfer the flow rate, and if you need more information on that, I'd be happy to follow up with you.
Well, yeah, and I can, I should say to all the attendees, we have, if you asked a question, we have your contact information. We can follow up with you after this Q&A. Another question asks, if you ran a 1.5 millimeter column on an unoptimized system, would you still see an improvement?
Yes, so that's a really good question. It really depends on how much dispersion your system has, whether you would see an improvement. So, like the example that I had shown earlier in the presentation, comparing a 2.1, a 1.5, and a 1, you did see taller peak response for the 1 millimeter ID column. The only trouble with it was it wasn't giving you the plates that you would like to see for that length column. So I guess if you had a critical pair that you're looking for resolution, the broader peak width could impact that. So you'll see some improvement, sure, but it just won't be as much as if it really were a truly optimized system.
And this question asks, isn't it true that smaller ID columns have lower efficiency?
So you would expect that, but for the work that we did in developing our 1.5 millimeter columns, we did having similar or just about as good efficiency as we see with our 2.1 millimeter ID columns as a goal, and I'm happy to say that we are able to meet that goal. So if you're comparing our 2.1 millimeter ID columns to the 1.5, you will see very similar efficiency, but not a huge difference like what we showed with a 1 millimeter ID column.
I'm looking to see if any other questions have come in here. Dr. Schuster, is there anything else you'd like to highlight or tell the attendees right now?
Oh, sure. So I think maybe some people are skeptical about how good really are these 1.5 millimeter ID columns, and I think in order to really answer that, you'd have to give them a try for yourself. So some feedback that we've been getting from customers is they're pleased with getting some 50% solvent savings and better peak response. Some other people, they're not really able to minimize their dispersion as much as they need, so they're not seeing as big of a impact when they go to the 1.5. So I think it really depends on really what your system is and what you're trying to separate.
We had question come in that asks, are there any special considerations when hyphenating with electrospray ionization mass spectroscopy?
Yes, there are actually. So one of the things that I didn't really get to go into really detail on is that when you're operating at a lower flow rate, you do need to optimize the source conditions. So that would be, running at a lower temperature and just really looking at optimizing your source conditions. So I would say that would be my recommendation.
Great. Let me see if any other questions have come in. And I'll tell the audience, again, you've got an email address on the slide in front of you if you have any other questions after this presentation. I think we've gotten to everything that's come in. Oh, let me see if there's one more here. I think we're good. So I want to say thanks again to Dr. Schuster for your fascinating presentation, and thank you participants for being a great audience. Be sure to check CNEN or CNEN Online for information on the next edition of CNEN webinars. Thank you On24 for technology and production services. And thank you Advanced Materials Technology for the sponsorship that made this interactive webcast possible. For CNEN webinars, I'm Jeff Huber, and I hope everybody has a great day.